Right, so let me start, of course, with thanking the organizers, thanking you for being here. I mean, I know this pizza thingy is great, but you know, I know how many people would be there without that, but that's a different question. Thank you for being here, and it's actually my first talk in Bonn, so I'm really particularly grateful for this opportunity. So I want to talk about q-Gaussian algebras. And of course, I have to start with q-Gaussian variables, which are very, very simple, right? I mean, so you have this family as q of h. So these all live in some algebra, which unfortunately is called gamma q of h, which whenever you have a group gives you a lot of trouble, right? You know, okay, what can I do? And what do we know about them? So this is supposed to be a 2-1 factor, at least in most of the cases we know. Probably if h is one-dimensional, so h here is a real Hilbert space, is real. And if you want to have a 2-1 factor, you should probably have dimension bigger than 2. And the only thing we know is this moment formula, right? So the sum of all pair partitions. So P2M stands for pair partitions. Then we have here Q to the number of inversions of sigma. And then we have what I should probably call H1 to HM sigma. That is the product over all ij in sigma, hi, hj. And since we have a real Hilbert space, that doesn't make a big difference. And the number of inversions is, okay, so how many inversions are here? None. Here's one. You know, we all know how to count, right? You know, whenever you draw a picture and there's a cross, that's an inversion, right? Very important here for our context that we are not just summing over the non-crossing partition. If we were to do that, my talk would be void, but it would be a different talk. So these are the q-Gaussians. There's actually another way to think about it. So, you know, when we studied our objects, which I haven't introduced, we realized that you also have something close to, what did I learn on Wednesday? Hypergraph. So you can think of taking the unit vectors here, always, you know, a part of the unit basis, right? So and then we have a word. Let me do this with indices. So these are the so-called Wick words. So for every such tuple, you know, if you replace, there is a word depending on the tuple, and then you can ask yourself, okay, if I have two such words, what is the product, right? I mean, you know, if you have a group, you want to know what is the product. And there is a formula which is independent of Q, sort of, right? So you sum over all partitions in 1, 2 partitions of the set from, the way I did this is M, you know, because I have altogether n M indices. And then we have here a number Q, which depends on sigma. We have here a product, H1 up to Hm, which only depends on the pairs in this partition. So 1, 2 partition means we have singletons and pairs. And what do? The pairs we need to construct the vector. So here we will take an inner product like this, but only about the pairs, right? So this is the inner product coming from the pairs, and we keep the singletons. Yeah, so these are the, R is the number of singletons, right? So there is actually a formula which almost looks like, you know, these are the linear coefficients. Here are the original words again. It's not really a hypergroup because there's a problem. If you repeat the indices, then there's some problem with the inverse or something like this. But it has this very, very fixed multiplication structure. So these are two ways to think about them. And so these are the scalar Gaussian algebras. And so what is the only difference, which I want to talk about today, We want to talk about algebras, operator valued. What should that be? Well, has Q of H in some Hilbert space, and of course also with some B's, right? So you have an algebra of B, and then you take the von Neumann algebra. So you have a B and a Q, and then you look for the algebras which is generated by some coefficients. And of course, you want to have some interaction between the Q's. And, if not, this would be boring. It would be a tensor product. It's one of the cases which is possible. And then, if this is in a von Neumann algebra M, which later we will probably call gamma Q of B and say H, then yes, you start to see that you have to make certain decisions, right? So if you have an SQ of H and a B, you can define maps. Right? So we start with an element in B. We send this in the large algebra. If this is a 2-1 factor, we can recondition back, and then we have these structure maps. Now, what happens in the case Q equals 0? Q equals 0. That's essentially something Dima considered. And if you start to just modify this formula, right? So let's modify this formula. You have an you add a B1 here, B m minus 1 here. Then you would get, of course, the same kind of coefficients. You would somehow expect to have the same coefficients. But then you get a term here which somehow has to depend on the input variables B, right? I mean, it's if you want to expect that for scalar coefficients there is no change, then the formula would have to change in this way. But you have to know what that function is, right? So at some point, you have to know this function. And that's kind of the little, picture philosophy here. What happens if here in the case Q equals 0, we would only cross over non-crossing partitions. And for non-crossing partitions, you inductively can apply this procedure. So the only thing you have to know is you want to calculate these kind of multilinear moments. Well, you put your B in between. You calculate this function here. Whenever you see such a pair, they're neighboring pairs. You contract them. You get that coefficients, and you have a formula with you. So it's completely determined for Q equals 0. And for Q not equals 0, this here gives you a lot of extra headache, because suddenly these Q's produce interaction terms, not only first order but second order, and so of course Q means it tails away. I mean, there's a geometric series, so it's kind of long-term interaction but mild long-term interaction. I think that's kind of the feeling you can get very quickly if you think about these algebras. What do we want to study? We want to study some von Neumann algebraic properties of these, right? So we are actually very strongly motivated. My co-partner here is Bogdan Udrea. He comes from deformation rigidity. He said, okay, let's take these algebras. Let's prove a nice theorem by Popper and Voss in the setting about deformation rigidity. Shouldn't be so hard, right? Well, okay. Now, yeah, very good. Okay, so it's joint work with Bogdan Udrea. I want to tell you a little bit about history of q-gaussians. It starts with the q-gaussian factorials. And then Kümmerer Speicher, they wrote an overview pair article with Kümmerer Speicher and Bojeka in 97, but Speicher and Kümmerer introduced the first version of the scalar q-gaussians. There's a nice paper by Guta-Maassen which generalized these kind of objects, and it's important for a reason you will see later. Then there's work by Kolak, generalized Yang-Baxter equations. And then, from there on, there are factoriality, matrix models, CMAP. Then, there was a big jump in for isomorphic. So for Q very, very close and the dimension very, very small, this is actually isomorphic to L of n with a wonderful machinery of Shlyahtenko and Guionnet. Then there are some results on type 3. And now there's also a paper by Nielsen Zhang where they consider QIJs with, not one fixed Q, but a family of QIJs. Did I do a misspelling? Yeah. Well, you know who's meant, right? So, and so what is nice is that they have an infinite dimensional object, which is isomorphic to the free group factor. But these QIJs have to go to 0 pretty fast in order to make that work. If not, it somehow doesn't work. So there's this question whether these guys are all isomorphic to the free group factor. And that's the motivation to consider operator value coefficients, because maybe with operator value coefficient, this task is easier or harder, or probably harder, and then maybe Voiculescu is not right. Whatever, right? So I told you about these formulas for partitions. And then for Q equals 0, Shlyahtenko's operator value q-gaussian really depend on completely positive map or family of completely positive map, or B of L2 values completely map. And what I wanted to tell you is this proposition, namely, if this matrix is Selfadjoint with respect to a given trace, there is a trace, a 2-1 factor. And I think that is really important, because if not, then we cannot really use techniques from finite for Neumann algebras. So how do we overcome this problem with these moments? And my philosophy is, well, in some sense, we should think of an algebra given by relations and generators. So the generators are clearly the q-gaussians and these generators, and we have to talk about the relations. And these relations, for me, are exactly the moments which I talked about here. And I have to define them in some way. That is kind of what took us a little while to find a way to define these guys in a consistent fashion. So that is something you have all seen. So how do we define such an object here? This actually we could only do using quantum probability in some sense. So here's the trick. We start with an inclusion B in A. A is some kind of algebra of coefficients. B is the algebra we are concerned about. And we start with a family of copies, right? So you send A into some data algebra, which we don't know much about. It's just a large space. And we call them copies. Well, if they're all, trace-preserving star homomorphisms. So that's fine. But we need some relations which allow us to make our moment formulas more manageable, and that's what we need symmetry for. So what is symmetry? Symmetry is very simple. You have all these different copies of the same variables in different positions, right? So they're indexed by natural numbers from the copies. If we have an bijection on n, we don't want these coefficients to change if we condition back on B. So these are symmetric copies. Yeah, so phi 1, 2, 1, 2 is the same as 5, 7, 5, 7, right? So you can change 1, 2, 1, 2 to 5, 7, 5, 7, but also to 7, 5, 7, 5, right? So this gives us some consistency, which we were looking for, pretty canonical. There's a good reason we haven't done that yet to understand something which is not symmetric, but subsymmetric or spreading. Why? Because then instead of representation of the symmetry group, we would have representations of the braiding group, and I think they're probably more interesting one than the one I have so far, but D is just another 2-1 for Neumann algebra, which is not very relevant. It's just an ambiente space so that we can talk about the objects, how they interact. It's just D stands for data, right? I mean, all our construction depends on all these data, but the algebra itself is not important. What is important is this function. Okay? Yeah, that will come in 5 minutes. But of course, yes. And so in order for technical reasons, what we also want to assume is some kind of strong independence of these algebras. Namely, if you take the algebras generated by an index set and the A's and the B's, then, so the B's are automatic because they're subalgebras. We want these conditional expectations to have a commuting square property Oh, that's a product, yeah. Yeah, that's a product. So that, and then we want this to be, yeah, and he's asking about it because the next royalty, he studied these tail algebras with Köstler, and there you can actually find examples of these properties if you work with these tail algebras, and that's an interesting topic in its own right. And Ken actually wrote some nice papers about this. So, so these are the properties we need, and then we can define these multi-moments simply by defining them as EB of a certain, copies. And copies here, if we have a certain partition and I say I1 up to IM less than sigma, then this means that the indices obey sigma, meaning they're equal if sigma tells them to be equal, and they're not if not, right? So I will use this notation quite a bit. No, I mean, no, it's exactly if and only if. But for this thing, I need that, right? Yeah, so whenever you have an action of a permutation group, you can produce such symmetric copies. If you take a stabilizer group of the first one, yes, for all ij. So this is a way to produce such copies. Still, I don't have enough examples. So if you have nice representations of the symmetric group, I'm still looking for, more than the canonical examples. This is what Dima said, right? I mean, you can take the tensor product representation and then copy the B as a tensor product. This is the easiest example. You can take free copies, and then it turns out that the Q in the construction will completely disappear. So what you also understand that we are allowing something which is between independent and free, and that is kind of what makes our headaches larger, because everything, well, you don't know exactly whether it's free. It has this kind of degree of flexibility, and you have to come up with something different. Anyway, yeah, and we will see some group examples later. So yeah, here is a technical thing. So in order to make these algebras well-behaved under the deformation, so the Gaussian algebras have always a deformation by functoriality. There's a Hilbert space, and then there's a number operator, and you can produce them. So we extend this to Hilbert space values functions. This is a technical extension, but it is actually helpful. And once we have that, then we can simply define our models using a procedure which was invented by Speich and used by Bian. So instead of defining the algebras, we're just defining matrix models right away. So in particular, if all the data is nice, then this will be properties which have the embeddability in the R omega. This is kind of built in. So what we do is we take these, so SQ of EJ, these are standard orthogonal vectors which follow the q-Gaussian distribution. We couple them with the Pj of A or Pj of F tensor A if you want to act a Hilbert space vector. And this limit behaves correctly, right? Only problem is we're always working in these large ultra products. So if you like ultra products, that's fine. If you hate them, then that's not so fine. So this is our algebra. Yeah. So we define and I want to insist that sometimes I don't have to take all of A, right? I mean, I can take a subset because often we are interested in finite dimensional pieces. So if you want a fixed notation, we have a subset of A and maybe a subset of a Hilbert space or a Hilbert space. And then we take all of these coefficients and the B's, and that is the algebra. We want, well, almost. I mean, so what we actually do is we will first do this for an infinite dimensional Hilbert space. Then we will close it up under the action of the, for a smaller space, we will have to close it up under the action of our number operator. So you will see that in a second. Okay. So so here's the moment formula, which you can prove using a central limit theorem. So the fact that we are tending n to infinity tells us that we only have, as before, we only have to sum over pair partitions. So that is unchanged. This is unchanged. The moment coming from the Hilbert space vectors, that's also unchanged. And here, the trace is in this D trace. And of course, this m sigma of x1 is just the product of these guys according to sigma. So we have a formula which is consistent and does not depend on any ultra product. So that's kind of nice, right? There's some convergence. But that is a standard application of the central limit theorem. Whenever you have such a central limit theorem and you divide by 1 over square root of n, there is some nice cancellation. So, however, these objects here, they somehow pop up, right? I mean, they are not scalars. They are operator-valued objects, and we have to deal with them. And this is actually kind of the key lemma. So let's start with, you know, the n version. Instead of, you know, we take a product of n elements of the form, and don't forget these were averages, right? So 1 over square root of n is q. So there were these averages from before. We multiply them out, and then we have the sum over all singleton or pair partitions. This is kind of a common feature that we have to allow singleton n pairs, because we are not just calculating the trace, we're also calculating the object. So singleton n pairs are natural. Everything else goes to 0 as n goes to infinity. That's the central limit theorem. Also well-known phenomena, that's not new. And so for a pair partition, we get this, you know, kind of lengthy expression, sum of all indices, which obey this thingy. And okay, this is just by definition, this is the object we have to consider, and we will call these objects turn out to be bounded as n turns to infinity for q less than 1. And the limit, we will call them Wick words, right? So this is just our definition of Wick words. Because the first problem you have, if you define these objects, is what? Where's the Hilbert space? All the other constructions, they start from a Fock space. In our construction, we don't have a Fock space. We are desperately in hope for a Fock space. In fact, if I may quote that, I had a wonderful talk by Bogdan, and he gave a talk with a lot of pictures. And in some place, he said, you know, my Hilbert space is here, right? We had to fight a long time to find the right Hilbert space. You know, it was not in our heart. It was, you know, hidden in these formulas. And we had to work for it. At the end, it is very clear. It's generated by these Wick words, and they have their canonical Hilbert, I mean, inner product. But there is something important. So, you know, I'm summing here over the pair partitions, which have singletons and pairs. And we have to understand the action of the deformation, right? The deformation usually in a Fock space counts the dimension of the underlying Hilbert space. And here, what we prove by using a little bit of martingale inequalities is that we can reduce somehow, we can somehow get rid of the pairs. Yeah, we start, if we have such a summation, then there are all these pairs. But, you know, there's another formula where we can get rid of the pairs, and then we get some pretty nasty looking objects. But at any rate, what happens is, yeah, we have a formula. I cannot really say more than there is a formula, right? There is some formula. But what is important is, I have this on the next slide, that if you have a Wick word, the heat semigroup, which is induced from the ultra product, only sees the size of the singleton and ignores the size of the pairs. Yeah, so the pairs, they are somehow descending at infinity. They're averaging out. And the reason for that is very easy. If you have one formula and you take an inner product with another such object, because of the moment formula, pairs, once they are paired, they cannot pair with another pair, because that would be a partition of order more than 2. So pairs cannot pair anymore. So they are, you know, that marriage is forbidden. And so that means that they have to sit alone, and that means that in average they disappear. But that's something one has to prove, right? That is the cardinality of the singleton in the singleton pair partition, right? Yeah, so exactly, right? So we have a singleton pair partitions. The pair partitions are kind of dummy variables, which only produce scalar coefficients. And the rest, they give these operator-valued averages, which we have to deal with. And and then the Hilbert space, you know, they're bounded for q less than 1. You have to prove this. And our Hilbert space, here it is. It's just the collection of all words of order k. And these guys are orthogonal, and these dks are in fact modules. And a posteriori, yes, they do behave like creation and annihilation, right? A single object can only create and annihilate 1 degree, so they have this, you know, off-diagonal form, right? So a posteriori, everything is fine. It's just that a priori, if we could have written down this Fock space to begin with, that would have been a different story, but our construction didn't allow for that. Okay, dk is a bimodule. And I think this was the state of the art when I visited Dima. And he told me, look, you know, In some cases, you have to make an assumption that certain things are finite dimensional, right? So you had some L infinity space in mind. Okay, it was a nice conversation. It's always have a nice conversation. It didn't help me much later, but it did help us a lot. much later, right? So we came up, sometimes you need spiritual motivation, and that it is. So first of all, we discovered that here we have the same multiplication rules, right? So a product of two weak words can be written in such a hypergraph fashion. Yeah, I come back to this comment later. So, and then, so here are some examples. Again, if you take the tensor product action, you get that's the tensor product of a gamma q. That's not big news. It's just telling you that these objects are in our category. We have to accept them. They are the free factors. And then, yeah, then we have another example. This is kind of cute. So what we do is, this is a slightly different construction, but it falls into the category after some massaging. So we do the following thing. We give ourselves a group action, G, for Neumann algebra B. And of course, G also acts on LG by conjugation or by left translation or not at all, right? We have three options, actually. And then we form some very funny variables. So I call this capital SQ of HG. So I take an SQ of H, so some Hilbert space vector. We always need these Hilbert space vectors to make sure that our big words behave well. So they're just dummy variables, but kind of useful for the investigation, not for the result, but for the investigation. And then I'm using this complex vector, lambda of G times the tracial vector. That's a complex variable, right? I mean, a group, usually they're not idempotents. And then I'm tensoring this with kind of another unitary, namely lambda G itself. So I'm just concatenating these two objects. I say, well, I cannot view them separately. They have to be combined. That's my rule. And then I get something like a weird cross product, right? I would get B, and then these SGs, which interact with B like group actions, right? So they interact very little. But of course, a little bit, right? So these are the three examples we understand at this moment, right? I mean, there could be some few more, which we're still trying, but these are some. And so let me tell you a little bit about these modules, because, we realize these modules are really important. In the first case, they are fat form, just the tensor product. In the free case, they're huge. We have no control over them. They're tremendously big. In this group case, we find something super interesting. So these modules, they create all commutators of the group. And why? Because you can take a pair and a pair and a pair and you intertwine them, like here. You iterate these intertwiners, and then you average them out by pairing them. And that produces commutators of the group, but only for Q not 0, because the crossing part don't allow these crossings. So here in terms of the module, they suddenly get bigger if Q is not 0, right? I mean, they have this commutator group popping up as extra coefficients, whether we like it or not. They just, there. And as you will see in a second, that's not good. But anyway, I mean, you do the calculation. You have to accept what you have. But there's at least one teeny bit of indication that maybe Q equals 0 and Q not 0 could be a little bit different. I mean, I don't know how to make capital out of this. But, this is kind of why we want to do this investigation. We want to see, I mean, are these things all the same or not? And here's a little bit of evidence of something being different. Yes, so for instance, if you take the whole group, you get the full commutator group. And if you taught something with the free group, the commutator group of the free group, oh man, that's still a big thing, right? It's actually pretty big, yeah? So it's not reducing things a lot. Okay, so these are the things we know, and here's our theorem. So some definitions. An algebra is called amenable with coefficients over B if there's an invariant state on B of L2n tensor B of prime. So usually if you talk amenable, you would have an amenable state on B of L2. But here you're reducing it to this algebra, which is the commutator of the opposite algebra, and you want to have an A invariant state on that algebra. And strongly solid, after, we are following, in some sense, we are, of course, following Popava's roadmap, right? We know what we have to prove, we just don't know how to do it. The roadmap is fine, but every little instant is kind of a little, a lot of hurdles on the way. So every detail is wrong, but the great concept is perfect, right? So it's strongly solid means if either A embeds into a corner of B, or the commutator of the normalizer is amenable over B. So that's the alternative which they use to prove that different actions of the free group are non-isomorphic. You can distinguish the number n and m from an action, from an ergodic action. So it's a strong technical result if you work. And here is where the conversation with Dima paid off. It just helped me to decide, okay, maybe I have to assume that this dimension is small. Because if it's too big, I just don't know what to do. Finite dimensional is enough to produce these kind of vectors which you use for technical reasons, kind of as witness of the non-amenability or amenability. But we even, for this, you see what happens compared to the free case is that in the free case, a word either starts with a letter or it doesn't, right? And that means that certain modules are coarsely embedding into other modules. If you take away kinds of constant vectors, you have some kind of coarse embeddings. Now, in the Q case, you don't have that. You have to throw away larger pieces, and then it becomes coarse, but you have to pay a price. So it only becomes coarse relative to certain things being small. So there's a give and take, and that is our condition. So, by the way, in the group case, this dimension would always be 1, right? So C to the K is small, but, well, that's what we can do. We can show that these are strongly solid. So, yeah, and then I have millions of questions. Here we go. So, first of all, we have another result. So this was somehow along the Popava's line, and then we saw some older paper about rigidity, relative rigid inclusions. So that works in this group case and gives some kind of a number of non-isomorphic examples of this type, right? So we have to use some work of Joanna to distinguish them, and actually another paper of Vas. So what happens is that if we analyze these algebras, the B, even if the B is originally commutative, it's no longer a massa. And sorry, I'm a little bit naive, but if you go away from a massa and Popper's rigidity program, well, you can throw away a lot. That's a big price to pay, and there are only very few papers which deal with regular, right? For different G, and you have to, you have to be super specific. You have to be careful with the action, and this is really a complicated construction because you have to essentially show that the equivalence relations are stably non-isomorphic. So this stably non-isomorphic is the price you have to pay for not having a massa. And we first were kind of a little bit optimistic, and then, but no, that kind of is very complicated, and we would like to see some more nice arguments because you do, and you have to even make a symmetric assumption. This guy is nice, and this guy has a lot of assumptions, and even then, we only can conclude if the equivalence relations are non-stably isomorphic in this sense, which Vas and his student used to distinguish Baumschlag-Soliton groups. So it gets really, even in the easy cases, it gets really technical. And part of that is, again, the Q property, right? Because there is this commutator group coming up, and we have to take care of that one, too. So this is another example. By the way, there is, in principle, a way to just look for a commutative space, a Z action, and do the construction. And I don't know, for a Z action, when the Q version of these Z actions, because they're not amenable anymore, when they're isomorphic or not. Even for a Z action on a commutative space, this Q-ified version There could be sometimes isomorphic or not, but I don't know when that is the case. I mean, so very easy questions are not clear anymore. Part of them because we didn't have time enough to think about them, or simply we didn't do it. So yeah, there is something new compared to what probably Udrea should have talked about, but whatever. So we can actually can prove that the infinite dimensional gamma q of A, so this is the scalar, is also strongly solid. And there we borrowed an argument from harmonic analysis. We use iterated retransforms. So the original roadmap there by Popovas does not apply. You have to come up with a different argument. And we need these iterated retransforms and some, you have to use this ideal that certain things are small compared to a certain ideal. And that, with these iterated retransforms, luckily enough, that works. And that's kind of a fun argument. And, you know, in that result there, you have to let them tend to 0. But, you know, if they're all the same, they cannot converge to 0. So that's not possible. And so yeah, that's one of these things. And yeah, we want to extend it to the subsymmetric case because they come up in iterated cross product of groups. And we have many nice examples of iterated subsymmetric, not symmetric spaces. They come up in iterated ultra products in a very natural way. So somehow if you think of central sequence and, you know, central sequence over central sequence over central sequences, this is an interesting structure. I mean, you have the subsymmetry for free, but you don't have symmetry. That's kind of the contrast. This is actually a non-commutative phenomena in terms of distribution. In the commutative case, they will be symmetric by, you know, subsymmetric implies symmetric. But no, not in, I mean, that fails if you take an iterated cross product of S3, right? You know, you can prove we have only evidence, by the way, which is numerical, but you have to calculate the eigenvalues of a 72 times 72 matrix. Yeah, we can somehow get nice if we use commutation relations from the rotation algebras. We can also find nice subsymmetric copies where now in the moment formulas here, we can produce some nice imaginary powers, which is kind of cool. All that is also subsymmetric territory, unfortunately. So that's something, yeah, it's, you know, it produces this, and it depends on the order. So it's kind of, but the modules are small. So they're kind of in principle good objects, but not so. We cannot hand them. We need a fusion rule, not in your sense, but there's an argument for q equals 0. There's work of Joanna, which I first thought didn't apply, but it actually does apply. So there, one can use a trick and use an argument of Joanna. So in the case q equals 0, without the dimension assumptions, these guys are strongly solid. But I cannot fuse this with this finite dimensional. So at the moment, there's a super large gap. I mean, sometimes they can pass to the limit, but limits are very delicate and can destroy strong solidity. That's known. So yeah, I told you these are many questions, right? So here they are. Then, of course, our real motivation is, I mean, here we have an algebra where we have relative CMAP, right? I mean, you know, because the gamma q's have them. So, but there is no definition for relative CMAP. I mean, we have it. It's, you know, you have it when you see it. But there, so far, I don't think there's a good definition. So it's a good example. And then, yeah. Does this machinery still continue to work in that case with b-valued coefficient or not? I don't know. Ah, yeah, that's a reminder. Can you read this? The photo is not as crisp as I want it to be, but I found it here around the corner, right? So I looked around the corner and I thought about, well, maybe we do have something in common, which is actually here, right? KMS. Sorry, guys, for some of you which don't like type 3, but communication with system. That's a reminder to thank the organizers for this incredibly nice workshop. Come on, I mean, we had really big lecture halls, so we should thank them. Okay. No. I found it after a beer, probably going out with you. But it's around the corner. You can find it today. I'm done. Yeah, come on.
So are there any questions from Marius? So you mentioned that the issue is sort of finding these S infinity actions.
Yes.
But I think there's sort of work of Vershnik or maybe his cohorts who did like they characterize characters on the
Yes.
sort of
But that's kind of action on the, I mean, you can always let it act on itself. But we looked at the modules and they grow. So unfortunately, we tried that, but it's not as nice as we want it to be. But yeah, so I need some mild actions, you know, a little bit of distortion, not too much. So these in between things are really not so, you know, almost commutative, but not really. That would be fantastic.